Tonight, we're going to talk about a collision that sounds distant, abstract, and safely theoretical, the future meeting of two galaxies. You've heard this before. It sounds simple. The Andromeda Galaxy is moving toward the Milky Way, and one day, far in the future, they will collide. But here's what most people don't realize. The word collision quietly activates the wrong intuition, and the word future makes the event feel optional, soft, and remote. Neither of those reactions survives contact with the actual scale involved. The distance between the Milky Way and Andromeda is so large that even light moving as fast as anything can take more than 2 million years to cross it. Not 2 million seconds, not 2 million days, 2 million full human histories stacked end to end, just to deliver a single snapshot from one side to the other. That distance is not empty waiting. It is already in motion. By the end of this documentary, we will understand not just that the Andromeda collision will happen, but why it cannot be avoided, what collision actually means at this scale, and how our everyday intuitions about space, motion, and time quietly fail long before galaxies ever touch. Our sense of cosmic safety will not be replaced with fear, but with a calmer, more accurate frame for the reality we already inhabit. Now, let's begin. We usually start with a picture, a spiral galaxy, graceful and complete, floating in a black background. The Milky Way is imagined as a stable home, a vast but settled structure. Stars orbit the center, planets orbit stars, and everything feels layered, organized, and slow. Motion exists, but it feels contained. This intuition is not wrong at small scales. Inside a solar system, gravity does produce long-term stability. Inside a galaxy, that sense begins to fail. The Milky Way is not sitting still. Every star you see in the night sky is moving, not drifting, not wobbling, but travelling through space at tens to hundreds of kilometers per second. The Sun itself moves around the galactic centre once every 230 million years. That sounds static only because our lifetimes are short. If we compress the Sun's orbit into a single year, it is moving faster than a rifle bullet, every moment, without pause. Andromeda is doing the same. It is not parked across the void. It is rotating, reshaping, absorbing smaller galaxies, and moving relative to us. The crucial point is this: the space between galaxies is not a neutral backdrop. It is part of the system. When two massive systems exist within the same gravitational environment, distance alone is not protection. It's tempting to imagine galaxies like solid objects on a collision course, like cars or billiard balls. That intuition fails immediately. A galaxy is mostly empty space. The distances between stars inside a galaxy are so large that even when galaxies pass through each other, direct star-star collisions are extremely rare. So when astronomers say collision, they are not describing impact in the everyday sense. They are describing gravitational interpenetration and long-term structural disruption. But even that explanation is too fast. Before we can understand inevitability, we have to understand motion at cosmic scales, because inevitability does not come from drama, it comes from patience. Right now, Andromeda is approaching the Milky Way at about 110 kilometers per second. That number feels small if you're thinking about light. It feels large if you're thinking about cars. Both reactions are misleading. What matters is not speed alone, but speed sustained over time without resistance. There is no cosmic friction slowing Andromeda down, no medium to push against, no braking system waiting at the midpoint. If Andromeda were moving at this speed for a single human lifetime, it would barely matter. In 100 years, it would advance a microscopic fraction of the total distance. This is where intuition relaxes. Nothing seems urgent, but galaxies do not get tired. They do not stop. They do not overshoot and correct. They move for millions and billions of years with the same calm persistence. Imagine walking toward a wall 1 millimeter per second. At first, the wall feels irrelevant. You could stop at any moment, but if you never stop, and nothing pushes you away, the outcome is not a question, it is only a matter of time. At galactic scales, time is abundant. The current separation between Andromeda and the Milky Way is about 2.5 million light-years. That number resists intuition, so we slow down. A light-year is not a measure of time, it is a measure of distance, the distance light travels in 1 year. Light circles the Earth more than 7 times in a single second. Even so, it needs over 2 million years to cross the gap between these two galaxies. Now we repeat that distance in another frame. If the Milky Way were reduced to the size of a coin, Andromeda would be several kilometers away. Not across the room, not across the city, several kilometers of open ground, with nothing solid in between. That emptiness feels safe, but gravity does not require contact. Gravity does not weaken to zero just because space looks empty. At these scales, gravity works quietly. It does not pull like a rope. It curves trajectories slowly, bending motion over enormous spans of time. Andromeda is not heading straight for the centre of the Milky Way like an arrow. Its path is shaped by mutual attraction, by past encounters, by the distribution of the invisible mass we cannot see directly. That invisible mass matters. The Milky Way and Andromeda are both embedded in massive halos of dark matter, extending far beyond their visible stars. These halos overlap long before any spiral arms touch. From the perspective of gravity, the collision has already begun, not in a dramatic way, in a mathematical one. This is where inevitability first appears not as destiny, but as trajectory. Astronomers measure Andromeda's motion not just across the sky, but toward us. That inward component has been confirmed repeatedly. The uncertainty is not whether Andromeda is approaching. The uncertainty is how the final approach will unfold. For a long time, scientists weren't sure. Early measurements lacked precision. The motion across our line of sight was hard to detect. It was reasonable, based on limited data, to imagine Andromeda might pass by at a safe distance. That idea made sense. It fit the intuition that galaxies are isolated islands. Better instruments removed that comfort. When we finally measured Andromeda's sideways motion accurately, the result was smaller than expected. Too small? There isn't enough lateral velocity to avoid capture. The two galaxies are gravitationally bound. Once that is true, escape is no longer an option. Bound systems don't negotiate, they evolve. Over the next few billion years, Andromeda will continue to approach. The sky will change slowly. Constellations will distort. Andromeda will grow larger, brighter, more detailed, not suddenly, so gradually that no single generation would notice, but the trend will be relentless. Eventually, the outer halos will merge completely, gas clouds will compress, star formation rates will change, orbits will stretch and warp, the galaxies will pass through each other, then separate, then return. This is not a single crash, but a long gravitational dance lasting billions of years. Calling it a collision is already a simplification, but calling it avoidable would be a mistake. What we understand now is this: given the current masses, velocities, and geometry of the system, there is no known physical mechanism that will prevent the merger, no hidden force waiting to intervene, no cosmic traffic rule enforcing separation. The equations do not allow for a clean escape. This does not mean everything is precisely predicted. The exact shape of the final galaxy, the fate of specific stars, the detailed timeline, those remain uncertain. But inevitability does not require precision. It requires constraint, and the constraints are already tight. At this point, we've replaced one intuition with another, not fear, not awe, but recognition. Large systems evolve slowly, but they evolve decisively. Stability is often temporary, even when it lasts longer than civilizations. We are not witnessing a rare event. Galaxy mergers are common. Most large galaxies bear the scars of past collisions. The Milky Way itself has absorbed smaller galaxies before. Andromeda has done the same. What makes this event feel special is not its uniqueness, but our location inside one of the participants. We live inside a moving system, inside a larger moving system, inside a universe where motion never truly stops. The Andromeda collision is not a disruption of that order, it is an expression of it. And this is only the beginning of what that realization forces us to confront. Once we accept that motion does not need urgency to be decisive, the next intuition to fail is the idea that distance itself is a kind of protection. We are used to thinking of separation as safety. If something is far away, it feels disconnected. At human scales, that works. At galactic scales, distance is not a wall, it is a delay. The delay matters, but it does not change the outcome. When we say Andromeda is approaching, we are not describing a straight line in empty space. We are describing a relationship between masses embedded in a shared gravitational landscape. Gravity does not turn on suddenly when objects get close. It does not wait. It operates continuously, even when its effects are too slow for intuition to register. At the current distance, the gravitational pull between the Milky Way and Andromeda is weak compared to the gravity-holding stars inside each galaxy. That sounds reassuring, but weak does not mean irrelevant. Over millions of years, a weak influence applied continuously reshapes trajectories. Over billions of years, it dominates. This is where human intuition quietly breaks. We are trained to notice acceleration, not persistence. A sudden push feels important, a constant, gentle pull feels ignorable. But galaxies respond to the second, not the first. Right now, Andromeda is already falling toward us, not falling straight down, not accelerating dramatically, but drifting inward along a curved path set by gravity. The Milky Way is doing the same, moving toward Andromeda's center of mass. There is no fixed reference frame where one galaxy is passive and the other is active. The system moves together. To understand why this matters, we slow down again. Imagine releasing two objects in deep space, far from everything else. They are separated by a large distance and given a small relative velocity toward each other. If nothing interferes, they will approach forever. Even if the initial motion is tiny, gravity adds to it. Slowly, continuously. There is no stable midpoint where attraction cancels itself out. Now stretch that process over billions of years, not with imagination, but with repetition. The same small inward drift, every second, for 1,000,000 seconds, then 1,000,000,000 seconds, then 1,000,000,000,000. At no point does the system check whether the distance is still large enough to stop. Physics does not contain that concept. The reason this feels counterintuitive is that we experience gravity in environments dominated by friction and resistance. When we roll a ball, it stops. When we throw something upward, it comes back down and settles. Motion feels temporary. In space, motion is the default state. Stopping requires an explanation. Continuing does not. The space between galaxies is not empty in the way our language suggests. It contains dark matter, sparse gas, radiation, and a gravitational field shaped by everything nearby. That field does not fade to zero between galaxies. It overlaps. The halos of dark matter surrounding the Milky Way and Andromeda extend far beyond their visible edges. Long before any stars come close, these halos are already interacting. This is not speculation. We infer the presence of dark matter because visible matter alone cannot explain how galaxies rotate or how clusters stay bound. The mass required to hold galaxies together exceeds what we can see. That extra mass is distributed in large, diffuse halos. When two such halos approach, they merge early, deepening the gravitational well of the combined system. Once that happens, the system becomes more tightly bound, not less. Energy is redistributed, orbits change, escape becomes harder, not easier. It's tempting to ask whether something could intervene. Could another galaxy pass by and alter the trajectory? Could cosmic expansion pull them apart? These questions are reasonable. They reflect an intuition that large systems are fragile, easily perturbed. At this scale, that intuition fails in both directions. Cosmic expansion does stretch space, but it does so uniformly, and its effect is strongest over vast empty distances between unbound systems. The Milky Way and Andromeda are not unbound. Their mutual gravity overwhelms the expansion at this scale. The space between them is not expanding in a way that would separate them. Instead, gravity dominates, drawing them together despite the overall expansion of the universe. As for external interference, the local group, the small cluster of galaxies that includes the Milky Way and Andromeda, is relatively isolated. There are other galaxies nearby, but none massive enough or close enough to reverse the binding energy of the pair. Minor perturbations may alter details, but not the fundamental outcome. This distinction matters. Inevitability here does not mean absolute certainty in every detail. It means robustness. The merger is not balanced on a knife edge. It does not require perfect conditions. It survives small changes. When astronomers model the future of the local group, they run simulations with slightly different starting conditions. They vary masses, velocities, orientations. The timelines shift, the paths twist, but the result remains the same. The two largest galaxies merge. This is how inevitability appears in science, not as prophecy, but as convergence across models. We pause here, because another intuition is about to fail the idea that a collision implies destruction. At human scales, collisions are violent, fast, and terminal. Two cars collide, and motion stops. Energy is released in a fraction of a second. The system simplifies abruptly. Galaxies do not behave like that. Their collisions are slow, diffuse, and creative in a mechanical sense. Stars mostly pass by each other without contact. Planetary systems are perturbed, but rarely annihilated. What changes is structure, not existence. During the merger, tidal forces will stretch the galaxies. Long streams of stars will be pulled outward. Gas clouds will compress and ignite bursts of star formation. The overall shape will distort, then relax, then distort again. Over time, angular momentum will be redistributed, and the final system will settle into a new configuration. This process takes so long that no single observer could witness it in full. It unfolds over several billion years. If we compress the entire merger into a single hour, the most dramatic changes still take minutes, not seconds. There is no moment of impact. There is no single frame where everything changes at once. This matters because it reframes risk. From inside the Milky Way, the Andromeda merger does not represent an impending catastrophe in the everyday sense. It represents a gradual rearrangement of the environment on timescales far exceeding biological relevance. But inevitability does not disappear just because the process is gentle. A slow river still reaches the sea. We return to distance one more time, because repetition is necessary. 2.5 million light-years is not just large, it is misleadingly large. It invites the intuition that far means forever. But in a universe that is nearly 14 billion years old, a few billion years is not exceptional. It is ordinary. The Milky Way has existed long enough for this interaction to matter. Andromeda has existed long enough for this interaction to matter. They have been moving toward each other for most of their histories. We are not early observers. We are not late observers. We are simply observers inside a long process. At this point, something stabilizes. The collision no longer feels like a headline. It feels like a consequence. Not because we are resigned to it, but because we understand why nothing is pushing it away. We have not yet talked about what the sky will look like, or where the sun will be, or whether Earth will still exist. Those questions come later, and they require even finer distinctions between what is observed, what is inferred, and what remains uncertain. For now, what matters is simpler. Two massive systems are bound. Their relative motion is inward. There is no known mechanism to reverse that binding. Given enough time which the universe has, the merger will occur. This is not drama. This is not fate. This is mechanics operating patiently at a scale where patience always wins. And with that understanding in place, we are ready to confront the next failure of intuition, the assumption that because something happens far in the future, it has no present reality at all. Once we let go of the idea that distance protects us, the next intuition to collapse is quieter and more stubborn, the belief that the far future is somehow less real than the present. We treat time like a curtain. What is behind it feels speculative, optional, or abstract. At cosmic scales, that distinction does not exist. Future motion is already encoded in present conditions. Right now, the Andromeda collision is not waiting to begin. It is already underway in the only sense that physics allows. Positions, velocities, and masses are already arranged in a configuration that evolves forward whether we pay attention to it or not. The future state is not imagined, it is computed. This is uncomfortable because it removes a familiar kind of safety. We often rely on time as a buffer. If something won't happen for billions of years, we mentally demote it. We place it in a category closer to fiction than to weather. But gravity does not categorize events by relevance. It integrates continuously. Every second that passes slightly changes the system's energy balance. Nothing resets. To understand why this matters, we narrow the frame. Instead of thinking about galaxies as wholes, we think about individual stars. Each star in the Milky Way follows an orbit shaped by the combined gravitational field of everything else. That field is not static. As Andromeda approaches, even from far away, the overall gravitational potential of the local group changes. The effect is tiny at first, so tiny that it feels safe to ignore. But tiny effects are not erased by time, they accumulate. Consider a star on the outer edge of the Milky Way. Its orbit is loosely bound. It responds more easily to external influences. Over millions of years, the slow deepening of the combined gravitational field subtly alters its path. Not enough to notice in a single orbit, enough to matter over hundreds of orbits. Eventually, some stars will be pulled outward into long tidal streams, tracing the invisible structure of the merger. This is not a prediction about a dramatic future event. It is a description of a present process stretched across time. We repeat the idea because intuition resists it. The collision is not a moment, it is an era. If human history were stretched to the length of this merger, the invention of agriculture would occur seconds ago. Entire civilizations would rise and fall during what feels like a pause in galactic motion. This mismatch between human time and cosmic time is the source of most misunderstanding. We expect causes and effects to be close together. We expect action and consequence to share a moment. At large scales, that expectation fails completely. The Andromeda merger will take several billion years from first close pass to final settling. During that time, the galaxies will oscillate through each other multiple times. Each pass redistributes energy. Each pass sheds angular momentum. Each pass brings them closer to final union. This is not because something new happens each time. It is because the same rules apply again and again without exception. At no point does the system ask whether it should stop. Another intuition collapses here, the idea that we need to observe something directly for it to be real. We will not witness the full merger. No observer can. Even hypothetical observers living for millions of years would see only fragments. But lack of direct observation does not weaken prediction when the governing rules are well tested. We have seen galaxy mergers in every stage across the observable universe. Some are just beginning, with faint distortions. Some are mid-process, tangled and luminous. Some are complete, leaving behind large elliptical galaxies with little internal structure. These are not simulations. They are observations of other systems at different points in time. Because light takes time to travel, looking far away is also looking back in time. When we observe a distant merger, we are seeing a process that may already be complete by now. The universe offers us a library of outcomes, spread across space instead of time. This is how we know the Milky Way-Andromeda merger is not a special case. It fits a pattern that repeats across billions of galaxies. The same mechanics apply, the same constraints hold, the same endings appear. At this point, we separate observation from inference because that distinction matters. We observe Andromeda's current position and velocity. We observe the mass distribution of both galaxies, including their dark matter halos. We observe the behavior of other merging systems. From these observations, we infer the future evolution of our own system using models grounded in tested physics. The model is not a guess, it is an extrapolation, and like all extrapolations, it carries uncertainty in detail but stability in direction. Where does that uncertainty live? Not in whether the merger happens, but in how chaotic the internal rearrangement becomes, which stars end up closer to the centre, how much gas forms new stars, whether the final galaxy retains a disk-like structure or becomes more spherical. These questions remain open because small differences in initial conditions can cascade over billions of years. But the boundary of uncertainty is well defined. There is no model consistent with current data in which the Milky Way and Andromeda drift apart forever. That option is already excluded. This brings us to another subtle failure of intuition, the belief that inevitability implies immediacy. We often confuse will happen with is about to happen. At human scales, those meanings overlap. At cosmic scales, they are completely separate. The sun will exhaust its hydrogen fuel. That is inevitable. It will not happen tomorrow. Both statements are true, and neither weakens the other. The Andromeda merger sits in the same category. It is not a threat. It is a future state already locked in by present conditions. We emphasize this because it stabilizes understanding. There is no countdown clock, no approaching deadline. The collision is not creeping closer in any emotionally meaningful sense. It is unfolding at exactly the rate dictated by gravity, indifferent to awareness. Now we address a common misinterpretation. When people hear that galaxies collide, they imagine stars crashing, planets destroyed, systems erased. That imagery comes from applying dense-scale intuition to sparse systems. Inside a galaxy, the average distance between stars is measured in light years. During the merger, most stars pass by others without ever coming close enough for direct interaction. What changes is not the survival of individual stars, but the architecture of the system. Orbits become elongated. The central region grows denser. Over time, the combined galaxy relaxes into a new equilibrium. Many stars will find themselves on different paths, but existence is rarely threatened. This distinction matters because it reframes the collision as a structural transformation rather than an explosion. The universe does not favour abruptness. It favours redistribution. We pause again to repeat the scale. Billions of years, not as a number, but as a condition. A time span so long that slow forces dominate completely. Any effect that persists without opposition becomes decisive. Any effect that relies on suddenness becomes irrelevant. The inevitability of the Andromeda merger does not come from violence. It comes from endurance. At this stage, our intuition has shifted. The future is no longer foggy. It feels like a continuation of the present rather than a separate realm. Motion is no longer something that happens only when we notice it. It is something that happens regardless. We are now prepared to confront an even deeper misunderstanding, the idea that space itself is a passive container in which events occur. That idea fails next, and when it does, the collision stops feeling like two objects moving toward each other at all. It begins to feel like a single system rearranging itself according to rules that never stopped applying. And that change in frame is necessary before we can talk about what close actually means at galactic scales. As soon as we stop treating space as a passive stage, another intuition quietly collapses the idea that objects move through space as if space itself remains unchanged. At everyday scales, this works well enough. Roads stay put while cars move, air stays put while birds fly. But at the scale of galaxies, space is not a backdrop, it is part of the system. The Milky Way and Andromeda are not travelling through an empty arena toward a point of impact. They are embedded in a shared gravitational structure that reshapes space itself. What we call distance is not just separation, it is a relationship defined by curvature, mass, and motion combined. This matters because it changes what getting closer really means. When we say Andromeda is approaching, we're not tracking a rigid object sliding across a grid. We're tracking how the geometry of the local group evolves. As the galaxies move, the gravitational field changes everywhere, including in regions that seem empty. Space responds continuously, not discretely. At human scales, this distinction is invisible. At galactic scales, it becomes decisive. The Milky Way is surrounded by a vast halo of dark matter, extending hundreds of thousands of light years beyond its visible stars. Andromeda has its own halo, comparable in size and mass. These halos are not thin shells, they are diffuse, overlapping clouds of mass that dominate the gravitational behaviour of the system. Long before any star in Andromeda feels a noticeable pull from a star in the Milky Way, these halos have already merged. From a gravitational perspective, the two galaxies have been interacting for a very long time already. The visible disks are late participants in a much larger process. This reframes closeness. The galaxies are not far apart until their spiral arms touch. They have been close, in the only sense gravity cares about, for billions of years. We repeat this slowly, because intuition resists it. At cosmic scales, proximity is not measured by contact, it is measured by influence. If two systems significantly alter each other's evolution, they are already close. That closeness increases gradually. As the halos merge, the combined gravitational well deepens. Orbits that were once stable become stretched. Stars on the outskirts feel a tug that was not there before. Gas clouds respond by shifting, compressing, or dispersing. Nothing dramatic happens at first. That is precisely why the process is misunderstood. Human perception is tuned to thresholds. We notice events when something crosses a line, when a sound becomes loud, when motion becomes fast, when change becomes visible. Galactic evolution rarely crosses such lines. It accumulates instead. To anchor this, we change frames again. Imagine a shallow valley forming beneath your feet, so slowly that you do not feel it. The ground does not crack. There is no moment of collapse, but over time, rolling objects drift toward the lowest point. The valley was always forming, even when it felt flat. The gravitational landscape of the local group is doing exactly this. The combined mass of the Milky Way and Andromeda is reshaping space into a deeper basin. Once inside that basin, stars and gas respond whether they know it or not. This is why the collision cannot be avoided by waiting. Time does not freeze conditions, it enforces them. Another intuition breaks here, the belief that motion requires a cause that keeps acting. We often imagine gravity as something that pulls actively, moment by moment. In reality, gravity sets initial conditions and geometry. Motion then follows naturally. The galaxies are not being dragged together like objects on strings. They are following the paths available to them in curved space. Once those paths converge, divergence is no longer an option without additional energy, and there is no external energy source available at this scale. This is where cosmic expansion is often misunderstood. The universe is expanding. Yes, space on large scales is stretching, but that expansion does not act uniformly on all systems. Where gravity dominates, expansion is suppressed. Galaxies, solar systems, even clusters of galaxies remain bound. The Milky Way-Andromeda system sits well within the regime where gravity wins. The expansion of the universe does not pull them apart. It is irrelevant to their relationship. The space between them is not being stretched fast enough to overcome their mutual attraction. This distinction is subtle but critical. Expansion governs the large-scale structure of the universe. Gravity governs the local rearrangement of matter within that structure. Confusing the two leads to the false hope that everything naturally drifts apart. At this scale, some things do not. Now we address another deeply rooted intuition that inevitability requires symmetry. We often imagine collisions as head-on, centered, balanced. The Andromeda merger will not look like that. It will be asymmetric, off-center, and messy. That does not weaken inevitability, and it strengthens it. Perfect symmetry would allow for special cases near misses, delicate flybys. Real systems are not symmetric. Their mass distributions are uneven. Their orientations differ. Their internal motions are complex. These asymmetries bleed energy out of ordered motion and turn it into internal rearrangement. Each close pass between the galaxies will transfer orbital energy into random stellar motion. This process is slow but irreversible. Once energy is redistributed this way, it cannot spontaneously reassemble into a clean escape trajectory. The system settles because disorder increases, not because anything explodes. This is another place where everyday intuition fails. We associate disorder with chaos and destruction. In physics, disorder often means stability. Randomized motion is harder to reverse than organized motion. Over time, the Milky Way and Andromeda lose the clean structure of two separate rotating disks. Their stars occupy a broader range of orbits. The final galaxy, sometimes called Milky-Way in informal language, will be larger, rounder, and dynamically hotter, not because something went wrong, but because that is how bound systems relax. We emphasize again this is not speculation layered on imagination. It is inference grounded in countless observed mergers. The universe has already run this experiment many times. We are simply located inside one instance. At this point, the word collision has almost lost its everyday meaning. What remains is a process of gradual convergence driven by geometry, mass, and time. Nothing dramatic is required. Nothing dramatic is expected. And now another intuition begins to loosen the idea that close must mean dangerous. At galactic scales, closeness is not about risk, it is about correlation. Systems that are close influence each other's evolution. That influence can be profound without being catastrophic. We are still far from discussing what happens to Earth, the Sun, or the night sky in detail. Before we can do that responsibly, we need one more shift in perspective. We need to understand how probability behaves in systems that are vast, sparse, and slow. Because when people ask whether the Andromeda collision threatens us, they are really asking the wrong kind of question. They're asking it with the wrong scale of probability in mind. And that intuition fails next. When probability enters the picture, intuition usually collapses all at once. We're used to probability in crowded systems traffic, weather, crowds, accidents. In those environments, many interactions happen quickly, and chance feels aggressive. At galactic scales, probability behaves differently. It becomes dilute, patient, and oddly forgiving. This matters because most fears about the Andromeda collision quietly assume a dense environment. They imagine many things close together, interacting violently. But galaxies are not dense, they are vast, sparse systems where distance dominates everything. Inside the Milky Way, the average separation between stars is several light years. Even in the densest regions, stars are so far apart that a direct collision between two stars during the merger is extraordinarily unlikely. Not unlikely in the everyday sense, unlikely in the sense that it can be effectively ignored. We pause here and repeat the scale, because the number refuses to settle. Several light years, light travels nearly 10 trillion kilometers in a year. Between one star and the next, there are years of uninterrupted light travel. That emptiness does not disappear when another galaxy passes through. It overlaps. So when we talk about probability, we must change the question. The relevant question is not will stars hit each other. The relevant question is, how does gravity redistribute motion in a sparse system over very long times? Once framed correctly, probability becomes manageable. During the merger, stars behave like independent particles responding to a changing gravitational field. Their paths curve, stretch, and reorient, but they almost never interact directly. The probability of a star being physically struck by another star is so low that even across billions of stars, it remains negligible. This is not a comforting statement designed to reduce fear. It is a mechanical consequence of scale. At human scales, collisions dominate outcomes because objects are large relative to their separation. At galactic scales, separation overwhelms size. Gravity replaces contact as the dominant interaction. We slow down again. Imagine two swarms of bees passing through each other in open air, each bee kilometers apart from the next. Even if the swarms interpenetrate completely, individual collisions are rare. What changes is not collision frequency, but the overall flow of the swarm. Galaxies behave more like this than like colliding solids. The analogy is only a scaffold. Once it anchors intuition, we discard it. What remains is the principle sparsity controls probability. Now we address the Sun, because it is the anchor point for most concern. The Sun orbits the centre of the Milky Way once every 230 million years. That orbit is not a fixed track etched into space. It is a response to the galaxy's mass distribution. As that distribution changes during the merger, the Sun's orbit will change with it. The probability question becomes how likely is it that the Sun ends up in a dramatically different environment? The answer is subtle. The Sun is not likely to be ejected from the galaxy entirely. That requires a strong gravitational encounter, which is rare in such a sparse system. It is more likely that the Sun's orbit will become more elongated or tilted, moving it farther from or closer to the galactic centre over time. But even here, likely must be handled carefully. There is no single future path for the Sun. There is a distribution of possible paths, all constrained within a stable range. This is where everyday probability intuition fails again. We are used to lotteries and coin flips, where outcomes feel discrete and dramatic. Galactic probability is continuous. Outcomes blend into each other. There are no sharp edges between safe and unsafe. Even if the Sun's orbit changes, the timescale matters. Changes unfold over hundreds of millions of years. Planetary systems adjust adiabatically, slowly, without violent disruption. Orbits stretch gradually. Stability is preserved precisely because change is slow. This is a general principle in physics. Systems respond differently to slow forces than to sudden ones. A sharp tug can break structure. A gentle pull applied for a long time reshapes it without destroying it. The Andromeda merger is defined by gentleness, not force. We repeat this because the word collision keeps dragging intuition back toward violence. Nothing slams, nothing shatters. Energy is redistributed, not released explosively. Now we confront another probabilistic misunderstanding, the idea that because something could happen, it therefore might happen in a meaningful sense. At cosmic scales, many things are technically possible but statistically irrelevant. Could a star pass close enough to the Sun to disrupt the solar system during the merger? In principle, yes. In practice, the probability is so low that it does not meaningfully increase during the merger compared to any other time in the Milky Way's history. The merger does not suddenly crowd stars together. It rearranges large-scale structure without collapsing local separations. This distinction matters because it separates imagination from inference. Science does not deny possibility. It ranks it. When astronomers simulate the merger, they track billions of particles representing stars and dark matter. They do not look for dramatic anecdotes. They look at distributions, how many stars change orbits, how density profiles evolve, how angular momentum flows. From these simulations, a stable picture emerges. The merger transforms the galaxy's shape and stellar populations. It does not turn the environment into a pinball machine. At this point, probability starts to feel less threatening and more descriptive. It is no longer about random danger. It is about constrained variation. We now zoom out again, because probability behaves differently at different scales. While individual stars are unlikely to collide, entire populations of gas clouds are likely to interact. Gas is different from stars. It is diffuse, collisional, and responsive to compression. When gas clouds from the two galaxies pass through each other, they do not simply pass by, they collide, shock, and compress. This triggers bursts of star formation. New stars ignite in regions where none existed before. This is one of the most observable signatures of galaxy mergers' increased starbirth, not because the universe becomes violent, but because compression becomes unavoidable. Even here, probability is constrained. Star formation does not explode everywhere. It occurs where conditions align sufficient gas density, cooling mechanisms, and gravitational instability. The merger increases the frequency of such conditions, but it does not guarantee them uniformly. This layered behavior stars largely unaffected individually. Gas dynamically active collectively is another place where intuition fails. We expect one rule to dominate. Reality uses different rules at different levels. We pause again to restate what now holds steady. The Andromeda collision does not meaningfully increase existential risk to individual stars or planetary systems. It does profoundly reshape galactic structure. Both statements are true simultaneously. If that feels contradictory, it is because we are still carrying human-scale expectations into a non-human system. Probability at galactic scales is not about danger. It is about inevitability without urgency and change without catastrophe. And now, with that probabilistic frame in place, we are ready to confront a deeper and more unsettling intuition, the idea that closeness in space automatically implies closeness in experience. Because even as the galaxies merge, most stars will never notice in any direct sense. Understanding why that is true requires us to rethink what interaction even means in a universe this large. And that reframing comes next. As we leave probability behind, a quieter intuition fails next the assumption that large events must be experienced locally to be real. We tend to measure significance by sensation. If something matters, we expect to feel it, see it, or be affected directly. At galactic scales, that expectation collapses almost completely. Most stars in the Milky Way will pass through the Andromeda merger without any local signal at all. No bright flash, no sudden gravitational jolt, no moment that marks before and after. From the perspective of an individual star, the universe will continue much as it always has, even while the galaxy as a whole undergoes a fundamental transformation. This is not a paradox, it is a consequence of scale. A star responds primarily to its immediate gravitational environment. Nearby stars matter more than distant ones. The collective pull of the galaxy matters, but only as a smooth background. During the merger, that background changes, but it changes slowly and coherently. There is no sharp boundary where one environment ends and another begins. So when we say the galaxies merge, we are not describing an experience. We are describing a statistical rearrangement. This distinction matters because it dismantles a deeply ingrained narrative instinct. We expect events to have centers. We expect proximity to correlate with impact. We expect closeness in space to translate into immediacy and effect. None of that survives here. Consider again the Sun. As the merger unfolds, the Sun will continue orbiting the galactic center, or rather, the evolving center of mass of the combined system. The gravitational forces acting on it will shift gradually as the mass distribution changes, but those shifts will be smooth. not punctuated. There is no moment when the Sun enters Andromeda's influence, because that influence has no edge. This is why the word close becomes misleading. When asked how close Andromeda will get, the intuitive answer imagines a distance measured between visible disks. But gravitational closeness is not about surfaces, it is about influence gradients, and those gradients extend far beyond anything we can see. We repeat this slowly. Two stars can be light years apart and still be part of the same dynamical process. Two galaxies can overlap visually, and yet most of their contents remain dynamically isolated at small scales. This layered reality is difficult to accept because it violates narrative compression. We want one thing to happen at one time in one place. The universe rarely obliges. Instead, the merger unfolds as overlapping processes operating at different levels. At the largest scale, dark matter halos merge early, reshaping the gravitational field. At the intermediate scale, stellar orbits are stretched and reoriented. At the smallest scale, planetary systems continue almost unchanged, insulated by distance and timescale. Nothing about this requires a dramatic local signal. This leads us to a critical reframing. The Andromeda collision is not an event that happens to stars. It is a process that happens to distributions. Individual stars are data points inside that process, not protagonists within it. Once this is understood, a common misconception dissolves. People often imagine that as Andromeda approaches, the night sky will suddenly fill with alien stars, dramatically brighter and closer. The reality is more restrained. Yes, Andromeda will grow larger in the sky over billions of years. Its structure will become clearer. Eventually, it will dominate the night sky. But this change will be imperceptibly slow on human timescales. No single generation will notice a shift. There will be no moment of surprise. And even when the galaxies interpenetrate, the sky will not become crowded in the way intuition suggests. The added stars will be distributed across vast distances. Brightness will increase slightly. Patterns will distort gradually. The sky will look different, but not chaotic. Again, this feels unsatisfying because it denies drama, but it aligns with everything we know about sparse systems evolving slowly. We now confront another intuition that quietly distorts understanding the belief that influence requires proximity in the present moment. In everyday life, causes are nearby in time and space. At galactic scales, influence is distributed and delayed. Light itself enforces delay. When we look at Andromeda tonight, we see it as it was over 2 million years ago. The galaxy we observe is not the galaxy that exists now. The stars we see shining are long gone or repositioned. We are always looking into the past. This delay is not incidental. It is fundamental. It means that even as the merger progresses, no observer inside either galaxy ever sees the current state of the other. Interaction happens through gravity, which propagates at the speed of light, just like information. Even gravitational influence arrives with delay. So when we speak of the galaxies responding to each other, we are describing a continuous exchange of influence that is always slightly out of date. The system evolves smoothly precisely because nothing updates instantly. This further erodes the idea of a decisive moment. There is no now in which the collision occurs. There is only a long interval during which conditions change incrementally. We repeat this because it is easy to forget. The merger is not synchronized. Different regions of the galaxies experience different stages at different times. What looks like early in one place may be late in another. There is no universal clock for the event. This is why the merger resists storytelling. Stories require simultaneity. Physics does not. Now we address the role of observers, because it reveals another failed intuition. We often imagine that being inside a system gives privileged access to its dynamics. In some cases, that is true. In this case, it is not. An observer inside the Milky Way does not see the merger more clearly than a distant observer. In fact, the opposite is often true. From outside, astronomers can see the entire structure, the tidal tails, the overall deformation. From inside, those same features are smeared across the sky, difficult to interpret. This is already true today. We struggle to map the Milky Way precisely because we are embedded within it. Dust obscures our view, perspective distorts structure. The merger will amplify this difficulty, not resolve it. So even as the galaxy transforms, local observers may perceive very little beyond subtle changes in stellar distribution and star formation rates. The largest transformations are global, not local. This is another place where intuition fails. We expect to feel big changes most strongly where we are. At galactic scales, the opposite can be true. The biggest changes are easiest to see from far away. This does not make the merger abstract or unreal, it makes it distributed. We pause again to stabilize what we now understand. The Andromeda collision is not a single moment. It is not locally dramatic. It does not announce itself. It unfolds across scales, affecting structure more than experience. If that feels anticlimactic, it is because we are still shedding narrative habits that evolved for a very different environment. Now, with experience decoupled from significance, we are ready to address another persistent misunderstanding, the belief that survival requires stasis. We often equate safety with things staying the same. At cosmic scales, stability often emerges through change, not in spite of it. Galaxies grow by merging. Stars form because gas clouds collapse. Planetary systems settle because energy is redistributed. The Andromeda merger is part of this broader pattern of evolution, not an interruption of it. This does not mean everything persists unchanged. Structures dissolve, others form, but the system as a whole remains coherent. Order is not destroyed, it is transformed. Understanding this requires us to stop thinking in terms of preservation and start thinking in terms of constraint. What constraints persist across the merger? Gravity, conservation of energy, conservation of momentum. These rules do not blink, they do not reset. Because these constraints hold, the system evolves predictably at large scales even as details remain uncertain. That combination, predictable direction, unpredictable detail, is the signature of complex but stable systems. At this point, another intuition loosens the idea that inevitability implies significance for us. The merger will happen whether or not life exists to witness it. Its importance is not measured by relevance to observers. It is measured by consistency with physical law. This realization is not meant to diminish human experience. It is meant to place it correctly. We are not central to the process. We are embedded within it. And that embeddedness has one more implication we have not yet addressed. While individual stars are largely insulated, entire populations like gas, dust, and star-forming regions are not. Their behavior shapes the future appearance and composition of the galaxy in ways that matter for long-term evolution. To understand that, we need to shift from stars to matter that can collide, compress, and cool. Because the most visible consequences of the merger do not come from stars meeting stars. They come from matter that behaves very differently under pressure. And that shift in behavior changes the galaxy in ways that persist long after the merger is complete. When we shift our attention from stars to gas, intuition has to be rebuilt almost from scratch. Stars are effectively collisionless. Gas is not. It flows, compresses, shocks, and radiates energy away. That single difference is responsible for most of what makes galaxy mergers visibly transformative. Interstellar gas occupies only a small fraction of a galaxy's mass, but it dominates its future. Gas is where new stars form. Gas responds quickly to changes in pressure and density, and gas does not ignore encounters. When two streams of gas meet, they interact immediately. During the Andromeda merger, vast clouds of gas from both galaxies will pass through each other. Unlike stars, these clouds cannot simply cross paths unchanged. They collide, slow down, and compress. Kinetic energy is converted into heat and then radiated away. Pressure builds. Regions that were once stable become unstable. This is the mechanical origin of merger-driven star formation. We pause here, because this is often misunderstood as a violent process. The word collision again invites imagery of explosions and destruction. In reality, gas compression is a controlled failure of balance. A cloud that was previously supported against gravity by internal motion loses that support. Gravity takes over. The cloud collapses, fragments, and forms stars. This is not chaos. It is structure emerging from constraint. The timescale still matters. Even rapid starbursts triggered by mergers unfold over tens or hundreds of millions of years. From a human perspective, that is eternity. From a galactic perspective, it is brief, but it is never instantaneous. As gas clouds compress, they cool by emitting radiation. This cooling allows them to collapse further, forming dense cores where nuclear fusion can ignite. New stars appear not because the merger adds energy, but because it removes it in the right places. This inversion energy loss leading to creation is another place where intuition fails. We are used to associating energy release with creation, and energy loss with decay. In star formation, the opposite is true. Losing energy allows matter to settle into tighter, more ordered configurations. The merger facilitates this by creating conditions where energy can be shed efficiently. Now we restate this with repetition, because scale matters. Two galaxies approach. Their dark matter halos merge first, deepening the gravitational well. Gas responds by flowing inward along distorted gravitational paths. Gas streams collide. Collisions dissipate energy. Dissipation enables collapse. Collapse produces stars. Each step is forced by the one before it. Nothing dramatic is required. No special trigger. Just time and gravity. This is why merging galaxies often appear bright and blue in astronomical images. Blue light signals young, massive stars. These stars burn quickly and die young. Their presence indicates recent star formation. The merger does not just rearrange existing stars, it temporarily changes the population. But this change is not permanent. Starbursts exhaust gas. Once the available gas is consumed or heated, star formation slows. The galaxy enters a quieter phase. Over time, the merged system often becomes dominated by older, redder stars. This long-term outcome is important. The Andromeda merger is not just an episode of increased activity, it is a transition toward a different kind of galaxy. The Milky Way and Andromeda are both spiral galaxies with organized disks. Disks require cold gas and orderly rotation. Mergers disrupt both. As angular momentum is redistributed and gas is consumed, the system loses the conditions needed to maintain a thin disk. The final galaxy is expected to be more spherical, with stars on a wide range of orbits. This is not destruction. It is relaxation into a new equilibrium. We emphasize again this outcome is not guessed. It is inferred from observing galaxies at different stages of merging across the universe. Many large elliptical galaxies show evidence of past mergers. Their structure, stellar populations, and dynamics carry memory of those events. In this sense, the Andromeda merger is not unusual. It is typical. Now we return briefly to Earth, not because Earth is central, but because it anchors intuition. The increased star formation during the merger will not bathe Earth in dangerous radiation. Distances remain vast. Even supernovae, which are rare and localized, will not suddenly become a threat simply because the galaxy is merging. This is another place where intuition exaggerates risk by ignoring scale. More stars form, yes, but they form far away, spread across enormous volumes. The probability of harmful proximity remains low. What does change is the large-scale appearance of the galaxy. From a distant observer's perspective, the merged system will glow differently. Its brightness profile will shift. its shape will smooth out. Over billions of years, it will fade as star formation declines. From inside, these changes are subtle and distributed. There is no global alarm, no universal signal. We pause again to stabilize understanding. Gas behaves differently from stars. That difference drives visible change, energy dissipation, not impact, powers transformation. Star formation is enhanced temporarily, then suppressed long-term. With that in place, another intuition is ready to fail the idea that the merger is primarily about two named galaxies meeting each other. In reality, the merger is about the evolution of the local group as a whole. Smaller galaxies are already involved. Some will be absorbed, others will be flung outward. The system does not consist of just two actors. It is a network responding to a deepening gravitational potential. This matters because it changes how we think about boundaries. The Milky Way is not a closed system. Andromeda is not a closed system. Their merger redraws the map of what belongs where. Dwarf galaxies orbiting the Milky Way today may end up on very different paths. Some may merge early, some may survive as satellites of the final galaxy, some may be ejected entirely. These outcomes depend on initial positions and timing, not on any central plan. Again, this is not chaos, it is sensitivity within constraint. At this point, we have accounted for stars, gas, dark matter, and structure. We have separated experience from significance. We have replaced collision imagery with gradual transformation. There is one major intuition left to dismantle before the picture becomes stable: the belief that inevitability implies prediction down to fine detail. It does not. Understanding where prediction ends and why that boundary exists is essential if we want a calm, accurate view of what science can and cannot say about the Andromeda merger. And that boundary comes next. As we approach the limits of prediction, intuition often reaches for certainty as a comfort. We want to know exactly what will happen, where everything will end up, and when. At galactic scales, that desire itself becomes the next intuition to fail. Inevitability does not imply exact foresight. The Milky Way-Andromeda merger is inevitable because large-scale constraints dominate its evolution. But within those constraints, small differences grow. This is not failure of knowledge. It is a property of complex systems evolving over long times. To see why, we slow down and narrow the frame again. Consider a single star orbiting within a galaxy. Its motion depends on the combined gravitational influence of billions of other stars, gas clouds, and dark matter particles. No single influence dominates. Instead, the star responds to a smooth, averaged field that emerges from countless small contributions. As the merger progresses, that field changes continuously. Each change slightly alters the star's path. Those alterations feed into future changes. Over hundreds of millions of years, tiny differences in timing and position accumulate into large differences in outcome. This sensitivity is not chaos in the everyday sense. The system does not become unpredictable all at once. It becomes unpredictable in detail while remaining predictable in form. We repeat this distinction carefully. The merger's direction is stable. Its final state, one larger, relaxed galaxy, is stable, but the exact path taken to get there is not. This is why simulations never produce identical results even when starting conditions are nearly the same. Small variations in initial positions or velocities lead to different tidal tails, different starburst timings, different orbital histories for individual stars. But across all simulations consistent with observation, the same large-scale story emerges. This separation between global certainty and local uncertainty is uncomfortable for human intuition. We're used to thinking that if a system follows laws, it should be fully predictable. That expectation comes from experience with short timescales and small systems. At large scales and long times, prediction becomes statistical rather than narrative. Astronomers do not predict the future of the Milky Way by tracking individual stars. They predict distributions, density profiles, velocity dispersions, luminosity functions. These quantities evolve smoothly and reliably. Individual trajectories do not. This is not a limitation of technology. Even with infinite computational power, exact prediction would still fail, because the system amplifies microscopic uncertainty, quantum-scale fluctuations, measurement limits, and numerical rounding all eventually matter when time is long enough. But this does not undermine understanding, it clarifies it. The right question is not, where will this star be? It is, what range of outcomes is consistent with known constraints? When framed this way, the merger becomes legible again. We apply this frame to the Sun. We cannot predict the Sun's exact orbit billions of years from now. We can predict that it will remain bound to the merged galaxy with high probability. We can predict that its orbit may become more eccentric or inclined. We can predict that it will not suddenly be flung into intergalactic space without an extremely rare encounter. These are not guesses. They are probabilistic statements grounded in dynamics. This reframing dissolves another intuition, the idea that uncertainty implies ignorance. In physics, uncertainty often marks the boundary between what is sensitive and what is robust. Robust outcomes persist across uncertainty. Fragile ones do not. The merger outcome is robust. The details are fragile. Now we address a common misunderstanding that arises here. When people hear that details are uncertain, they imagine that anything could happen. That is not true. The range of possible futures is narrow compared to the space of all imaginable futures. The Sun will not suddenly reverse direction. The galaxy will not fragment into chaos. The laws of motion still apply. Conservation laws still constrain every interaction. Uncertainty lives within those walls. We pause and repeat, because this stabilizes intuition. Uncertainty does not mean unpredictability everywhere. It means predictability at the right level. This distinction is not unique to galaxies. It appears in weather, fluid dynamics, and ecosystems. Large patterns persist even when small details fluctuate. The merger is another expression of that principle. Now we confront another subtle intuition failure, the belief that models are speculative because they refer to the future. In everyday reasoning, future claims feel weaker than past observations. In physics, future behavior can be as well constrained as past behavior when the governing rules are known. We have not observed the Milky Way-Andromeda merger directly because it has not completed, but we have observed mergers at every stage in other systems. We have tested gravity across many regimes. We have validated numerical methods against observations. The models used are not extrapolations into the unknown. They are interpolations across a dataset spread through space and time. This is why scientists speak calmly about the merger, not because they are indifferent, but because nothing in the physics suggests a dramatic deviation. At this point, inevitability has been stripped of drama, fear, and mystery. What remains is constraint-driven evolution. But one intuition still lingers, the idea that inevitability requires a clear timeline, a date, a countdown. People ask, when will it happen, expecting a moment? The answer resists that format. The merger does not occur at a single time. It unfolds across an interval measured in billions of years. First close approach, first separation, second approach, final settling. Each phase blends into the next. There is no universal clock that marks completion. Even defining collision becomes ambiguous. Is it when halos overlap, when disks pass through? When the final galaxy relaxes, each definition yields a different time. This ambiguity is not a flaw. It reflects the continuous nature of the process. So when astronomers say the merger will happen in about 4 to 5 billion years, they are compressing a long evolution into a single reference point. That number is useful, but it is not precise in the way everyday dates are precise. We emphasize this because it prevents misinterpretation. There is no day on which the sky suddenly changes. There is no threshold after which the universe is different. Change is always already underway. With this understanding, the future stops feeling like a separate category. It feels like the present extended. And that prepares us for the next shift in scale, where the Andromeda merger is no longer the dominant story at all. Because beyond the merger lies a larger context in which even this event becomes one step in a much longer evolution. And understanding that context is necessary if we want to know what inevitable really means in a universe that itself is changing. As soon as we place the merger inside a larger context, another intuition gives way the belief that the Andromeda collision is the dominant event in the Milky Way's future. It feels enormous only because we are close to it in scale. Beyond it, there are processes so slow and so large that even galaxy mergers become intermediate steps. The Milky Way and Andromeda exist within the local group, a small gravitationally bound collection of galaxies. The merger will reorganize that group, but it will not end the story. The combined galaxy will continue to orbit within a larger cosmic structure shaped by dark matter on even grander scales. This matters because inevitability is not absolute. It is always relative to a frame. Within the local group, the Milky Way-Andromeda merger is inevitable. Beyond the local group, other structures obey different constraints. On the scale of galaxy clusters, mergers continue. On the scale of the observable universe, expansion dominates. Different rules matter at different levels. We slow down again to anchor this. The universe is expanding, and that expansion is accelerating. Over time, distant galaxies will recede faster and faster, eventually moving beyond our ability to observe them. This does not affect bound systems like the Milky Way-Andromeda pair, but it does define the horizon beyond which interaction is impossible. This introduces a subtle but crucial distinction. Some futures are inevitable because systems are bound. Others are impossible because systems are unbound. The local group is bound. Its members will continue to interact, merge, and rearrange. But beyond a certain scale, expansion wins. Galaxies outside the local group will drift away, never to be encountered. Their futures diverge permanently from ours. This does not negate the merger, it contextualizes it. After the Milky Way and Andromeda merge, the resulting galaxy will likely absorb or interact with most remaining local group members. Over tens of billions of years, the local group may collapse into a single massive galaxy, surrounded by a sparse halo of remnants. From the perspective of the far future, the Andromeda merger will look like an early step in that consolidation, not a final act. This reframes inevitability again. The merger is not the endpoint of motion, it is part of a cascade of gravitational settling. Now we introduce a limit, carefully and calmly. There is a point beyond which prediction truly fails not because of chaos, but because the universe itself changes character. As dark energy drives accelerated expansion, regions of space become causally disconnected. Information can no longer pass between them. In that regime, future loses its usual meaning, not philosophically but physically. Events outside a bound region cannot influence it, ever. The universe fractures into isolated islands of matter. The Milky Way-Andromeda merger happens well before this isolation becomes dominant locally, but the final galaxy will live in an increasingly empty universe. Over time, the night sky will grow darker as distant galaxies slip beyond the cosmic horizon. This is not speculation, it follows directly from measurements of cosmic expansion. We repeat the frame. The merger is inevitable because gravity dominates locally. Isolation is inevitable because expansion dominates globally. Both are true at once, depending on scale. This layered inevitability is difficult to hold intuitively. We prefer one story at a time. The universe does not comply. At this stage, the merger stops feeling like a singular destiny and starts feeling like a consequence of hierarchy. Small systems settle quickly. Larger systems settle slowly. Some never settle at all. The Milky Way and Andromeda are small enough, relative to the universe, to settle together. Now we return briefly to the present, because this perspective can feel abstract. Right now, stars continue to orbit, gas continues to cool, dark matter continues to shape motion invisibly. Nothing in daily experience reflects the merger, because daily experience is confined to scales where change is minimal. This is not a failure of awareness, it is an alignment between scale and perception. We emphasize again, inevitability does not mean urgency. The merger does not rush toward us. It proceeds at exactly the rate allowed by gravity and distance. With this in mind, another intuition dissolves the belief that inevitability implies significance for action. There is nothing to prepare for, nothing to prevent, nothing to accelerate. The merger is not a problem to solve. It is simply a description of how matter behaves when given enough time. This calm framing matters because it separates understanding from reaction. Science does not demand response, it demands coherence. At this point, the Andromeda merger is fully embedded in a multi-scale picture local gravity, group dynamics, cosmic expansion. Each level constrains the next. None contradicts the others. And now, with the largest context in place, we are ready to return inward to the question that opened this entire discussion. How close is the Andromeda collision? Not in distance alone, but in time, in influence, and in inevitability. Because answering that requires one final recalibration of intuition, understanding what close even means when human scales no longer apply. And that final recalibration comes next. When we ask how close the Andromeda collision is, intuition immediately reaches for a ruler or a calendar. We want a distance. We want a date. Both answers exist, but neither satisfies, because neither matches how closeness works at this scale. Closeness, in human terms, is about imminence. Something close is something about to happen. Something distant is something safely deferred. At galactic scales, closeness is not measured by urgency, it is measured by constraint. Right now, Andromeda is about 2.5 million light-years away. That number sounds enormous, and it is, but it is not large compared to the forces involved, and it is not large compared to the time available. In a universe nearly 14 billion years old, a few billion years is not remote, it is typical. We repeat this slowly. The merger is not close in the way tomorrow is close. It is close in the way adulthood is close to childhood. It is already embedded in the system's trajectory. There is no alternate branch where it does not occur. This is why asking how close in kilometers or years misses the point. The more meaningful question is how constrained is the future, and the answer is highly constrained. The Milky Way and Andromeda are gravitationally bound. Their relative motion is inward. There is insufficient sideways velocity to escape. No external force is available to intervene. These facts already define the outcome. In that sense, the collision is as close as it can be without having already happened. We pause here because this reframing is subtle. We are used to thinking that distance delays relevance. At this scale, distance delays observation, not outcome. The outcome is already fixed by present conditions. To anchor this, we change frames again. Imagine watching a slow avalanche begin high on a mountainside. At first, nothing seems to move. A single pebble shifts, then another. The final collapse may be hours away, but the slope has already failed. The rest is timing. The Andromeda merger is like that, except the slope failed billions of years ago when the system became bound. Everything since then has been follow-through. Now we examine time more carefully, because time is where most misunderstanding hides. Astronomers estimate that the first close pass between the Milky Way and Andromeda will occur in roughly 4 billion years. The final merger will take another 1 to 2 billion years after that. These numbers are approximate, not because of ignorance, but because the process has no sharp boundaries. What does first close pass mean? Is it when the visible disks overlap, when the distance between centers reaches a minimum, when tidal distortions become prominent? Each definition yields a different time. None is wrong. None is complete. So when we say 4 billion years, we are compressing a long gradient into a single reference point. That compression is useful, but it must not be mistaken for precision. This matters because human intuition treats dates as commitments. Cosmic processes do not. 4 billion years is also not an abstract number. It is comparable to the age of the Earth. The Earth formed about 4.5 billion years ago. Complex life arose much later. Entire evolutionary histories fit comfortably inside that interval. So while 4 billion years feels impossibly far in personal terms, it is not far in planetary or galactic terms. It is a familiar span. We repeat this again because repetition is necessary. The collision is not distant in cosmic time. It is well within the lifespan of stars like the Sun. In fact, it coincides roughly with the Sun's own future evolution into a red giant. This coincidence is not causal, it is contextual. It reminds us that far future does not mean after everything ends. It means after many things continue. Now we address another intuition, the idea that closeness increases steadily. We imagine Andromeda creeping closer at a constant pace. The reality is more complex. The approach is not linear. As the galaxies draw nearer, gravitational attraction increases, the relative velocity changes, the path curves. After the first pass, the galaxies will actually move farther apart again before returning. Closeness oscillates before resolving. This oscillation confuses intuition because it looks like retreat. It is not. It is energy redistribution. Each pass converts ordered orbital motion into internal motion. Each pass reduces the system's ability to separate cleanly. So even when the galaxies appear to move apart after the first encounter, the merger is progressing. Closeness is increasing in a deeper sense, even as distance temporarily grows. This is another place where everyday language fails. Moving away sounds like avoidance. In bound systems, it can be part of convergence. We emphasize this because it prevents a common misunderstanding. The merger does not fail if the galaxies separate after the first pass. That separation is expected. It is part of how the system loses energy. So how close are we now, really? We are close enough that the outcome is fixed. We are far enough that nothing dramatic is imminent. Both statements are true simultaneously. This duality is uncomfortable because we like closeness to imply consequence. At galactic scales, consequence can be guaranteed without being immediate. Now we shift to influence because influence often matters more than distance. The gravitational influence of Andromeda on the Milky Way is already present. It has been present for billions of years. It will grow stronger, but it does not switch on suddenly. There is no threshold where influence begins. So if closeness is defined by influence, then Andromeda is already close. This reframing matters because it dissolves the idea that the merger is something waiting beyond a boundary. There is no boundary. The system is already interacting. We return briefly to observation, because observation shapes intuition. When we look at Andromeda through a telescope, we see a serene spiral galaxy. It does not look like a threat. It does not look like a participant in a dramatic future event. That calm appearance is accurate. The merger does not require agitation, it requires patience. Even if we could accelerate time and watch the merger unfold, it would not look like an explosion. It would look like slow deformation, stretching, overlapping, and settling, motion without urgency. This is why the word collision is so misleading. It suggests speed and impact. The reality is closer to drift and capture. We now connect this back to inevitability, because closeness and inevitability are often conflated. Something inevitable feels close because we cannot avoid it, but inevitability does not compress time. It compresses possibility. The Andromeda merger is close in possibility space. There are no plausible alternatives. That is the most important sense of closeness here. This distinction is not semantic. It is structural. When scientists speak confidently about the merger, they are not claiming foresight into details. They are recognizing that the system has already chosen its path. We pause again to stabilize this understanding. Distance delays experience. Time delays observation. Neither delays constraint. At this stage, the question, how close is the Andromeda collision, has transformed. It no longer asks for a number. It asks for a frame. And the frame is this: the merger is already encoded in the present, unfolding slowly, indifferent to attention, constrained by laws that do not weaken with distance or time. There is one final intuition left to confront before this picture becomes complete: the idea that inevitability must feel heavy or threatening to matter. It does not. The Andromeda merger matters not because it endangers us, and not because it carries meaning, but because it is a clean example of how the universe behaves when given enough time. Understanding that behavior leaves us not alarmed, but oriented. And with that orientation, we are ready to return to where we began without adding anything new, only seeing the familiar idea with rebuilt intuition. And that return begins next. By this point, inevitability has lost its weight. It no longer presses on us as a looming event. It has become a background condition. That shift signals another intuition quietly dissolving the idea that understanding something inevitable should change how we feel about the present. At human scales, inevitability often carries urgency. Aging, deadlines, danger, these compress attention. At galactic scales, inevitability does the opposite. It stretches attention. It removes the need for reaction. Nothing about the Andromeda merger demands preparedness, concern, or response. The system does not register intention. It responds only to mass, motion, and time. This is not detachment. It is alignment. We return again to the present moment, not to center it, but to place it correctly. Right now, stars in the Milky Way continue their orbits. Gas clouds continue to cool. Star formation proceeds at its ordinary pace. The gravitational influence of Andromeda is already present, but it is weak and diffuse. It does not interrupt anything locally. This continuity matters because it corrects a common misinterpretation. People sometimes imagine the merger as a future change to reality. In truth, it is an extension of the same processes already underway. Nothing new will begin when the merger starts. Nothing new will end when it finishes. The same rules apply throughout. This realization dismantles another intuition that large-scale understanding should produce a sense of scale-induced insignificance or drama. It does not. It produces normalization. The universe is not waiting to surprise us. It is repeating itself. We emphasize this because repetition is the key to stability. Galaxy mergers are common. Star formation cycles are common. Gravitational settling is common. The Milky Way-Andromeda merger is notable only because of our position inside one participant. From elsewhere in the universe, this event would not stand out. Now we examine language itself, because language often smuggles intuition back in. Words like collision, crash, and impact carry emotional freight. They imply suddenness and damage. At galactic scales, they mislead. A more accurate description would be gravitational coalescence, but even that suggests a moment of completion. In reality, the process has no clean boundaries. The merger begins before we name it. It ends long after we stop talking about it. This is why astronomers speak carefully. They do not say the galaxies will hit. They say they will merge. Even that is a convenience. We pause again to repeat what now holds firm. The merger is inevitable. It is slow. It is distributed. It is non-violent at local scales. It is transformative at structural scales. Holding all of that at once is the goal, not emphasis on any single aspect. At this stage, another intuition dissolves the belief that inevitability implies finality. We tend to think of inevitable events as endpoints. The merger is not an endpoint. It is a transition. After the Milky Way and Andromeda merge, motion does not stop. Stars continue to orbit. Gas continues to evolve. Dark matter continues to dominate mass. The resulting galaxy continues to interact with its environment. The universe does not reach a resting state. This matters because it reframes inevitability as continuity rather than closure. The future is not a wall, it is a slope. We now revisit something we set aside earlier, the difference between observation, inference, and modelling. We observe Andromeda's current motion. We infer its future based on gravity. We model that future using simulations. Each step adds structure without inventing drama. The confidence in inevitability does not come from a single method. It comes from convergence, independent observations, independent models, and independent physical principles all point in the same direction. When that happens in science, calm replaces speculation. This calm is not indifference, it is own stability. We emphasize this because the Andromeda merger is often presented as a spectacle. In reality, it is a textbook case. It demonstrates how bound systems behave when left alone for long enough. Nothing about it is exotic. Now we examine one last intuition that still quietly interferes the idea that because something is inevitable, it somehow defines the meaning of what comes before it. At human scales, inevitability often frames narratives. Childhood leads to adulthood. Preparation leads to outcome. The merger does not frame the present that way. The present does not exist in service of the merger. Stars do not orbit in anticipation. Gas does not cool in preparation. Processes unfold because they are constrained to unfold. This distinction removes narrative gravity. The merger does not pull significance toward itself. Understanding this matters because it prevents retroactive distortion. We do not reinterpret the Milky Way's history as leading to the merger. The merger is simply one configuration change among many. The Milky Way has merged before. It will merge again in smaller ways. This event is not singular in function, only in scale. We pause again to stabilize this perspective. Inevitability does not confer purpose, it confers predictability. With that in place, we're almost ready to conclude. But before we return fully to the opening idea, there is one final clarification to make. It concerns limits. Science can say the merger will happen, it can say roughly when, it can say how the system will behave at large scales, it cannot say everything. And acknowledging that boundary is not a weakness, it is part of the rebuilt intuition. Because knowing where understanding ends is as important as knowing where it holds. And that boundary is the last thing we need to see clearly before we finish. At the boundary of understanding, intuition often expects mystery. It expects darkness, speculation, or a dramatic admission of ignorance. What actually appears is something quieter, a clean edge where questions change character. Science does not stop at that edge, it changes what it asks. For the Andromeda merger, the boundary is clear. We know the governing laws, we know the masses involved to within useful limits, we know the current motion well enough to constrain the outcome. What we do not know are the exact histories of individual components inside that outcome. This is not because those histories are hidden. It is because they are not stable enough to predict. We pause here, because this distinction is essential. Unknowns at this scale are not gaps waiting to be filled. They are features of systems where small differences grow over long time. No amount of future measurement will turn those details into certainties. That is what we don't know means here. We don't know which specific stars will be flung into long tidal streams. We don't know the exact orbit the Sun will trace through the merged galaxy. We don't know the precise shape of the final stellar halo. But we do know the range within which those outcomes must fall. This is a different kind of knowledge than everyday intuition expects. It is not narrative knowledge. It is constraint knowledge. Constraint knowledge tells us what cannot happen. The Milky Way will not remain a thin spiral disk forever. Andromeda will not pass by without lasting interaction. The system will not spontaneously unbind itself. These exclusions matter more than detailed forecasts. At this point, intuition often protests. It asks why we should care about inevitability if details are unknowable. The answer is simple and mechanical, because inevitability describes the structure of the future, not its texture. We repeat this slowly. Structure is stable, texture is variable. The structure of the future local group is that it contains one dominant galaxy rather than two. The texture exact stellar arrangements, transient features, temporary bursts of star formation will vary and fade. This framing is what allows science to speak calmly without overreach. It does not pretend to see every detail. It does not retreat into vagueness. It holds the boundary cleanly. Now we examine one more intuition that tends to distort this boundary, the belief that unknowns imply missing forces or surprises. At galactic scales, that expectation has little support. The physics governing the merger is well tested. Gravity behaves as expected at these scales. Dark matter behaves consistently with observation, even if its fundamental nature remains unknown. No new force is required to explain the dynamics. No anomaly demands revision. This does not mean new discoveries are impossible. It means they are not required for understanding this process. The Andromeda merger does not sit at the frontier of physics. It sits comfortably inside it. That placement matters because it removes suspense. The merger is not a test of unknown laws. It is an application of known ones under extreme scale. We pause again to stabilize understanding. When science says we don't know here, it is not gesturing at mystery. It is marking where sensitivity overwhelms specificity. This is why uncertainty does not accumulate as we project forward. It saturates. Beyond a certain point, additional time does not make predictions worse. It simply keeps them probabilistic. That saturation is another unfamiliar concept. We expect uncertainty to grow without bound. In many systems, it does not. It reaches a stable envelope defined by constraints. The Andromeda merger lives inside such an envelope. Now we address the final intuition that still quietly lingers, the belief that understanding inevitability should change how we interpret our place in the universe. That belief is tempting, but it is not required by the physics. The merger does not reposition us conceptually. It does not elevate or diminish human experience. It does not assign significance. It simply exists as a consequence of mass and motion. Science does not ask us to feel small or large. It asks us to be accurate. Accuracy, in this case, means recognizing that vast processes can be predictable without being immediate, transformative without being violent, and inevitable without being meaningful in a narrative sense. This recognition is not an ending, it is a settling. We have removed the last layers of false intuition that inevitability implies urgency, that uncertainty implies mystery, that scale implies drama. What remains is a stable frame. The Milky Way and Andromeda are approaching because gravity requires it. They will merge because nothing prevents it. The details will vary because complexity demands it. None of this asks anything of us. It simply describes the environment we already inhabit. With that understanding in place, there is only one thing left to do. Return to the familiar idea we began with and see it clearly, without distortion, for the first time. Tonight, we started with a familiar idea that the Andromeda Galaxy is on a collision course with the Milky Way. It sounded dramatic, distant, and safely abstract. Now, after moving slowly through scale, time, probability, and constraint, that idea has changed shape. Nothing about it is dramatic anymore. Nothing about it is abstract. The collision is not a headline waiting to happen. It is a condition that already exists. When we say Andromeda is coming toward us, we are not describing a future surprise. We are describing the present state of a bound system unfolding exactly as physics requires. Distance does not weaken that requirement. Time does not soften it. Nothing about patience makes gravity negotiable. The galaxies are close in the only way that matters. Their future has no alternative. That sentence now lands differently than it would have at the beginning. No alternative does not feel ominous. It feels mechanical. It does not imply urgency. It implies stability. The Milky Way and Andromeda are doing what massive systems do when left alone for long enough. They are redistributing energy. They are relaxing into a new configuration. They are following constraints that do not care how large the numbers become. The word collision no longer suggests impact. It suggests overlap, capture, and settling. The galaxies will not strike each other. They will pass through, distort, separate, and return. They will lose the ability to remain separate not because of violence, but because separation becomes energetically impossible. From inside the system, this process does not announce itself. Stars do not feel alarms. Planetary systems do not register a turning point. Even the sky changes too slowly for any single observer to notice. The merger is real, but it is not experiential. That distinction matters. At the beginning, intuition wanted a date, a distance, a moment. It wanted to know how close the collision was, as if closeness implied immediacy. We now understand why that intuition fails. At galactic scales, closeness is not about time remaining. It is about freedom remaining. There is no remaining freedom in this system. The Milky Way cannot escape Andromeda. Andromeda cannot escape the Milky Way. That constraint already exists, quietly, right now. Everything else is detail. We also understand why inevitability here does not demand attention. Nothing needs to be done. Nothing can be changed. Nothing is threatened in any meaningful local sense. The merger is not a risk to manage. It is not a future to prepare for. It is simply a description of how matter behaves when gravity is given billions of years to work. This is why the event feels both enormous and calm at the same time. Enormous in scale, calm in consequence. We now see clearly what was hidden at the start. The Andromeda collision is not a special moment in the universe. It is not a climax. It is not even unusual. Galaxies merge all the time. Most large galaxies are the products of earlier mergers. Our own galaxy has done this before and will do it again. What made this collision feel different was never the physics. It was our position. Being inside one participant made the event feel personal. Being human made the timescale feel unreal. Being accustomed to dense, fast systems made the word collision feel violent. Those intuitions no longer apply. What applies instead is a quieter frame. Systems evolve toward lower energy states when nothing prevents them from doing so. That is the entire story. Dark matter halos overlap and deepen the gravitational well. Gas responds by flowing and compressing. Stars respond by adjusting their orbits. Disks dissolve. Spheres emerge. Not because something goes wrong, but because this is how bound systems settle. Even the uncertainties now sit calmly in place. We do not know which stars will end up where. We do not know the exact shape of the final galaxy. We do not know the precise orbit the Sun will trace billions of years from now. And none of that matters for understanding what will happen. Those unknowns live inside a boundary that does not move. The merger will occur, the system will relax, the local group will consolidate, the universe will continue expanding beyond it. This is not mystery, it is resolution. When we say inevitable now, it no longer sounds heavy. It sounds descriptive. It is the same inevitability that governs the orbit of the Earth, the cooling of stars, the settling of gas clouds. It is not destiny. It is constraint. At the end of this descent, the opening idea looks smaller but clearer. How close is the Andromeda collision? It is close enough that the outcome is already fixed. It is far enough that nothing urgent follows from that fact. Both statements are true at the same time. This balance is the rebuilt intuition. We do not live in a static galaxy. We do not live in a fragile one. We live inside a system that changes slowly, predictably, and without regard for narrative. The Andromeda merger is part of that change. It does not define our present. It does not threaten it. It simply continues beyond it. This is the reality we live in. We understand it better now, and the work continues.